Let's investigate another type of limit. Let's look at the limit as x approaches 0 of 1 over x squared. Well, the problem here with trying to evaluate this limit is, if I were to just plug in 0, I'd get 1 over 0 squared. I can't divide by 0. What happens graphically is as we approach 0 from either the left or the right, the function just blows up. It just shoots off the graph. What happens algebraically is this. If I plug in plus or minus 1 over x squared is 1. If I plug in a smaller number, plus or minus 0.1, the result is 100. I plug in plus or minus 0.01 and I get 10,000. I put in plus or minus 0.001, I get a million. In general, I can make 1 over x squared as big as I like by sticking in a really small number for x. As x gets small, x squared is even smaller, and the reciprocal of a small number is really big. So as I approach 0, these numbers get arbitrarily large. What I'm going to say here is that this limit is equal to infinity. According to our strict definition of limit, this limit does not exist. These values are not approaching a number. But since they're not approaching a number in a very particular way, they are getting arbitrarily large without bound. We're going to say that it goes to infinity. So here is the definition of an infinite limit. We write that the limit as x approaches c of f of x is equal to infinity to mean that we can make the values of f of x as big as we like by taking values of x close enough but not equal to c. Similarly, we can write that the limit as x approaches c of f of x is negative infinity if the function goes down. Specifically, that means that we can make f of x as big in the negative direction as we like by taking x close to but not equal to c. Let me explain what I mean by big in the negative direction. I don't like talking about negative numbers as getting small when I go down. For example, negative 1 million is a smaller number than negative 10. But in a sense, I feel like it's really a bigger thing. You know, if I owed you $10 versus owing you $1 million, I'd care a lot more about owing you $1 million than about owing you $10. That's a bigger debt. So when I talk about numbers going off to negative infinity, I talk about them being big in the negative direction. We can also have one-sided limits that go to infinity. A common example is the log function. The natural logarithm, as x approaches 0 from the right, goes down to negative infinity. This is the graph right here. We see as we go to the right, the function ever so slowly gets to infinity. As we go to the left, it shoots down. It never hits 0 because the natural log is not defined for 0 or for negative numbers, but this curve down here gets closer and closer to the axis, the y-axis, and the values of the function shoot down to negative infinity. I can make log of x as big as I want in the negative direction by taking a really small positive number. Now note that this graph, y equal to the natural log of x, approaches the line x equal to 0, which is the y-axis. And when I say that, I mean that as we go further and further down, the curve and the line are virtually indistinguishable. You can't tell one from the other. We call this a vertical asymptote. This graph is asymptotic to that line. And the fact we have is that the graph of y equal to f of x has a vertical asymptote at x equal to c precisely when the limit as x approaches c, possibly from the right or left, of f of x is equal to plus or minus infinity. All right, so now let's find the vertical asymptotes of the function x over x minus 2. Now, in general, when I write a function as a ratio of two functions, vertical asymptotes are only going to occur when the denominator is equal to 0. So in this case, that's only going to occur when x minus 2 is equal to 0, i.e. when x is equal to 2. So let's analyze the behavior as we approach 2. We should be careful and see what happens as we approach 2 from the left and as we approach 2 from the right. Okay, as we approach 2 from the left, the denominator x minus 2 approaches 0 from the left. That is, it's going to be a negative number that approaches 0. So when we look at the limit as x approaches 2 from the left of x over x minus 2, that means we're looking at a positive number, which is what x is, over a negative number, which is getting smaller and smaller. So positive number being divided by a smaller and smaller negative number is going to be something that's going off to negative infinity. As x approaches 2 from the right, x minus 2 will be approaching 0 from the right. So the limit as x approaches 2 from the right is going to be the ratio of two positive numbers, one of which is approaching 2, and the other of which is getting smaller and smaller and smaller. So again, when I take the reciprocal of a really small number, I get something really big, and so this is going to approach infinity. Great. So as a result of either of these facts, it's good enough for one of them to hold true, but in this case we've got both. F of x has a vertical asymptote at x equal to 2. Let's look at the graph. And this is the graph of y is x over x minus 2. We see that as we approach 2 from the left, the graph goes down to negative infinity. As we approach 2 from the right, the graph goes up to positive infinity. And the graph on both ends approaches this vertical asymptote at x equal to 2. Now let's find the vertical asymptotes of tangent of x. Tangent is the ratio of sine and cosine. It's sine over cosine. So that means that the vertical asymptotes are only going to be able to occur when the denominator, which is cosine, is 0. That happens when x is plus or minus pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc. It's the odd multiples of pi over 2. Now, tangent is periodic with period pi, so each of these roots, each consecutive, root of cosine is separated by pi, so it's good enough for us to just say what's happening at pi over 2. As x approaches pi over 2 from the left, sine of x is going to be approaching 1, and cosine of x is going to be approaching 0, but it's going to be approaching it from the positive direction because to the left of pi over 2, cosine is positive. So it's going to be approaching 0 from the positive direction. So when I look at the limit as x approaches pi over 2 from the left, I have a positive number approaching 1 over a positive number that's approaching 0. So it's going to be a positive number that's going to infinity because I've got something going to 1 being divided by something that's getting arbitrarily small. So this goes to infinity. As x approaches pi over 2 from the right, sine goes to 1 again, but cosine goes to 0 from the negative direction. That's because cosine of cosine of x is less than 0 for x slightly bigger than pi over 2. So these values will be negative and getting closer to 0. So when I take the ratio, I have a positive number divided by a negative number, so I'm left with something negative, and the denominator is going to 0, which means that I'm taking the reciprocal of a really small number, which means it's really big. So I get a really big number in the negative direction, and as I approach pi over 2 from the right, tangent goes to negative infinity. Since tangent has period pi, we therefore have when c is equal to plus or minus 2 pi over 2, plus or minus 3 pi over 2, plus or minus 5 pi over 2, etc., that the limit as x approaches c from the left of tangent is infinity, and that the limit as x approaches c from the right of tangent is equal to negative infinity. Look at a graph of tangent to verify that this is what happens. We also therefore have vertical asymptotes at x equal to plus or minus pi over 2, x equal to plus or minus 3 pi over 2, x equal to plus or minus 5 pi over 2, etc. So for your third question for these videos, find the vertical asymptotes of cotangent of x by doing the same sort of thing using limits. And hint, to do this, write cotangent as a ratio.